Cameron Eaves, Airframe Team, Safety Pilot. Brady Moon, Autopilot Team, Antenna Pointer. John Akagi, Autopilot Team, Ground Station Operator. Andrew Torgeson, Autopilot Team Lead, Team Captain. Jake Johnson, Imaging Team, Imaging Detection, Localization, and Classification. Connor Olson, Imaging Team, Airframe Calibration. Brandon McBride, Unmanned Ground Vehicle Team, Imaging Detection, Localization, and Classification. Derek Knowles, Unmanned Ground Vehicle Team, Imaging Detection, Localization, and Classification. Tyler Miller, Imaging Team Lead, Networking and Interop. Jacob Willis, Unmanned Ground Vehicle Team Lead, Battery Manager. Ryan Anderson, Airframe Team Lead, Plane Launcher. Tyler Critchfield, Airframe Team, Airframe Assembly. The chosen airframe for our system is the Nimbus Pro, an off-the-shelf fixed-wing airframe from my flight dream. This airframe is fairly simple to assemble, which allows for quicker repairs and rebuilds in the event of a crash during development. The airframe has ample storage to fit all of our components, including the UGV and parachute for the airdrop portion of the mission. Its large wing area allows the system to fly slower than normal to capture clear images and more easily navigate waypoints and avoid obstacles. The wing clips also make for fast assembly and easy portability. 56 propeller designs were analyzed for combined propulsive efficiency with our motors and necessary thrust supplied. The GWS slow-fly 8x6 propellers were selected with an efficiency of 40%. The airframe was modeled in XFLR5 to analyze aerodynamic efficiency and ensure static and dynamic stability during flight. In this analysis, it was determined that the plane needed to have 7.5 degrees of tail incidence in order to fly without trim in steady flight conditions. A foam wedge was inserted underneath the tail to increase the tail incidence and provide pitch stability without excess trim. The UAS is comprised with the following electrical components: the Odroid XU4 computer, which functions as the onboard processing unit, the Flip 32 Plus Naze board, which is used as the onboard autopilot flight controller, the Inertial Sense Micro INS, a GPS-aided inertial navigation system, the RC receiver, a 900 MHz long-range transmitter receiver combo, the Sony a6000, a 24 megapixel digital camera. At an altitude of 150 feet, it provides 3 pixels per inch resolution of ground targets. The Ubiquity Bullet, which enables wireless communication between the ground station and the UAS, the GPS, the pitot tube and digital sensor, which digitally provides the UAS's airspeed, the EFLA 405 serverless payload release, which will be used for the UGV drop in the competition. All of these systems are powered using the Multistar 10,000 mAh LiPo battery. The autopilot system is run using ROS-Plane, an autopilot program created by the BYU Magic Lab, using ROS and augmented by this year's BYU AUVSI autopilot subteam. To address the object detection, classification, and localization problem, a server-client architecture was created. The architecture allows any number of autonomous and manual vision clients to classify images while also being easy to set up and maintain. The imaging server holds a definitive final copy of a target image, as well as a history of its state during intermediate detection, classification, and submission steps. This makes it easier to identify bugs and replicate results. The BYU AUVSI team is planning to attempt all mission tasks and is confident in completing all tasks except for the UGV drive task. The UAS has flown in over 35 flight tests, 17 of which were autonomous, and 3 full mission tests. The system has consistently completed waypoint navigation, obstacle avoidance, object detection, classification and localization, and payload delivery. Several kinds of testing were performed during the development of the UAS. These included unit tests of software and hardware, individual subsystem tests, integrated system tests, flight tests in simulation, and flight tests in hardware. Unit tests were performed during the development of each subsystem. Testing software and hardware in units facilitates the identification of failure points as well as opportunities for improvement during development and improves productivity. Subsystem testing was performed before full system integration, since errors are easier to isolate in the smaller subsystem environment. Integrating subsystems together always adds an added complexity. Subsystems can interact in unexpected ways, such as GPS interference caused by a USB 3 connection. It is important to test the fully integrated system to know exactly how the UAS will perform in June. Developmental software testing was performed in simulation. Doing so saves time setting up hardware for a flight test and mitigates the risk of damaging hardware. This is an effective approach for early stage development. For simulation testing, we used a high-fidelity environment in Gazebo, capable of modeling the flight dynamics of our aircraft, collisions with obstacles, the full autopilot software stack, and even sensor measurements imbued with random noise and biases. When it comes down to it, there's no better way to prepare for the competition than by testing the UAS hardware in flight. This kind of testing most closely mimics the conditions that will be experienced at the competition. For hardware testing, the same software components tested in simulation were used during actual flight tests. This pattern of testing is made possible by the modular and widely compatible nature of ROS, the backbone of our autopilot. The team conducted 17 autonomous flights with an average of 5 minutes spent in manual mode per flight. To tune the autopilot gains, a straight course heading was commanded to the airplane while in manual mode. The safety pilot switched control to the autopilot and the behavior was observed. Control was then taken back by the safety pilot and gains were adjusted accordingly. This process was repeated until the desired control response was observed in flight. This process was repeated for different wind conditions and with different commanded maneuvers. Waypoint accuracy was tested in both simulation and hardware. An RRT algorithm was used to build a path through all the waypoints while remaining in bounds and avoiding obstacles. For the first round of testing, 5 waypoints were randomly generated along with 10 obstacles. A simulated aircraft with aerodynamic parameters matching our aircraft hit 24 of the 25 waypoints with an average miss distance of 1.2 feet for each hit waypoint. A similar test was then performed using our competition airframe where it was able to hit 4 out of 4 waypoints with an average miss distance of 17 feet. In simulation, 10 obstacles were randomly generated over 5 tests. Out of the 50 total obstacles, 49 were avoided. Continuous integration tests were performed during development of the imaging software. This consisted of unit tests for all database access methods including select, insert, and delete functions. Whenever a software update was performed on the server, a batch of unit tests were automatically run and the commit would not publish if any of the unit tests failed. Next, integration testing was performed to ensure the client REST library interacts well with the server. The stream rate was tested first on the ground by sending images at various distances from the camera setup, resulting in a stream rate of about 1.5 to 2.5 Hz. This was further tested on the plane in flight. After improving the data compression method, the in-flight stream rate was 1 Hz. From flight test data, the average resolution of objects was found to be 3 pixels per inch at 150 feet altitude. Testing of the autonomous detection and classification algorithms was done by feeding images with or without potential targets through the algorithms and monitoring the output. These test images were collected by placing targets on the ground in a location with visual features similar to those of the competition field and imaging these targets with a drone camera at an altitude similar to what will be experienced during the competition. The results of the testings are as follows. Color identification was not tuned correctly when running these tests. With proper color tuning before the competition, we expect the color accuracy to be near 70%. Localization testing was first performed using a single target from a 4th-story window and resulted in a localization error of 20 feet. It was tested again from a 4th-story window onto a field with 9 targets in one image frame. Localization error was found to be correlated to the distance from the center of the image plane, increasing as the targets got further away. The drop mechanism was first tested by dropping a weight and parachute from a height of 2 stories, and then at a height of 50 feet for proof of concept and to project accuracy. Next, a servo-operated bay door was built into the UAS and tested in the lab at a height of approximately 8 feet. With this confidence, a model was developed for testing on board the UAS in simulation. It was then tested in hardware from an altitude of 120 feet. The result was an average accuracy of 53 feet. Over the course of development, 10 payload drops had been attempted in flight, during which the UGV survived 9 out of 10 times. In 3 full mission tests, autonomy and waypoint capture, obstacle avoidance, object detection and classification, and the UGV drop were tested. While autonomous takeoffs and landings have yet to be attempted, the infrastructure to do so is in place and should be ready well before the competition in June. The autonomy and localization portions of the imaging section are still under development and have not yet been attempted in a full mission test, though the team is confident that these will be ready by the competition. The drive to location portion of the airdrop section has not yet been attempted. While not completely comprehensive, the full mission tests conducted provide significant coverage of the competition requirements and have illuminated several areas of improvement. One flaw exposed during these missions was the time to set up our network connection. The network has occasionally refused to connect in the past, but the issue was never fully resolved. During one full mission test, the network refused to connect, halting the entire mission. It was hypothesized that the Wi-Fi connection from the router was interfering with a connection to the plane. After disabling the conflicting frequency, the network was restored. Another flaw encountered was a failure of the parachute to deploy after a drop. This was due to a minor oversight in the parachute packing procedure. A provision was consequently added to the pre-flight checklist to ensure this packing error is not repeated in the future. Another design flaw discovered during full mission testing was the debilitatingly slow image stream rate. Upon further investigation, it was discovered that images were not being compressed. After adjusting the imaging platform to compress images, the stream rate improved from 1 image every 30 seconds to 1 image every second. Based on results from our full mission tests and other testing, we achieved an average total mission score of 63%, with a projected June competition score of 75%.